The gravity of the time is such that every new avenue of peace, no matter how dimly discernible, should be explored. Never before in history has so much hope for so many people been gathered together in a single organization. You will provide a great share of the wisdom, of the courage, and the faith which can bring to this world lasting peace for all nations and happiness and well-being for all men.
My name is Charlie Cole. Welcome back to another episode here of Titans of Nuclear. Today we're talking to Brent and Lex Huntsman of Solid Atomic, who are developing a solid-state nuclear energy system, and we're excited to talk with them about it. Brent and Lex, welcome. It's great to have you guys on.
Thank you. Thanks for having us.
Yeah, of course. Awesome. So yeah, I think we'll start how we often start on Titans episodes, which is just a little about your guys' background. So I think I'll maybe ask both of you, and you can go one by one. Maybe we'll start with Lex and then Brent and switch it up later. But yeah, tell me about where you guys grew up. Were you interested in science as kids? Just tell me a little bit of background about yourselves, starting with Lex.
Yeah, sure. So I grew up in Northern California, and yeah, interested in science as a kid. Yeah, I mean, my favorite toy when I was like 3 was, I think, an extension cord, is what my parents tell me. So yeah, I've always been into energy. I'm a former Navy nuclear submariner. I served on the USS Los Angeles and operated the reactor plant there. So I've got hands-on experience operating nuclear reactors, and absolutely, I loved it. I really did. But I left because I wanted to get into design engineering, and the Navy doesn't do that.
Yeah.
So I've been, working professionally as an engineer for 15 years, and recently, in the last few years, I've been really engaged in wanting to sort of break the deadlock of nuclear energy in North America and really kind of globally, and get the technology moving again. Kind of bring us back to like 1959 and say, okay, let's pretend the anti-nuclear movement didn't happen.
Sure.
And go from there. And so that's me.
Very cool. What initially got you interested in the Navy nuclear path? Like, how did you first hear about nuclear? And
so I've known about nuclear energy for a while before the Navy, but I was just dead set on going into the Navy after high school because it's kind of a family history thing. My great grandfather was a commanding officer of a net tender during the Pearl Harbor bombing, and in fact, I served out of Pearl Harbor, so I was actually able to see the house that they lived in was still standing, and I'd heard stories as a kid of like my grandfather and his brothers and sisters like running and hiding in like a bomb crater in the sugarcane field, which is now the parking lot of the Navy Exchange.
oh my God.
And so so I got to see that house, and actually like literally right like a couple of months before I completed my term and honorably discharged, they condemned that block of housing and we're going to tear it down. So it's like, it was just really cool to like, I literally got to see it like
right.
Yeah. And when I kind of took the ASVAB, the Navy was just like, you are like nuclear program material. And I was like, obviously that's awesome. Like, I want to do that, and I'm like double down submarines. Yeah. I grew up watching Next Generation. So, I was like, the idea of being in a vessel where, you're alive and well on one side, and then on the other side of the bulkhead is certain death was just, I don't know, always appealing to me.
Yeah.
So,
did you ever think about space travel? Did you ever want to be an astronaut? I feel like that's that concept to the max. Just
absolutely. I definitely space is probably my, my first love, aside from energy. Those are kind of, space and energy are kind of it for me, and just engineering really cool things.
Yeah, totally. Cool. And then I think we can pivot over to Brent and we'll dive into everything more as well. But Brent, yeah, tell me a little more about your background. Where did you grow up? How did you were you excited about science as a kid? That's always my favorite question, is like the I think the kid, like the pivot from like children's interest in science to like real adulthood and like engineering is like such an interesting pathway to me. So yeah, tell me about it, Brent.
Yeah, I grew up in Oregon, in an area called Westland, Oregon, and we had a very good public education system there, and a museum, a science museum called OMSI that had like space camp and lots of things to teach you about. Back then, there was a nuclear power plant in Oregon called the Trojan nuclear plant. It's been closed since then. And so I had early exposure to just a wonderful science education, a lot of AP classes in high school. Went to Cornell University, and again, back then there was a nuclear lab called the Ward Lab that produced nuclear medicine, and of course provided some training. It's since been torn down and relocated.
Was it a full research reactor, or what was that?
Yeah, I don't quote me on this. I think it was a Triga reactor, but I don't remember. It's been quarter century. But then I went to UCLA for my graduate work and PhD, and I think I was accepted in the nuclear program, and then they took away, meaning the whole program, in the summer before I got there. So I ended up just studying as a mechanical engineer for all three of my degrees. Went to Anderson Anderson School of Management for a minor in like an MBA with a lowercase m while I was at UCLA, getting my doctorate, while working for NASA and doing future space flight, the nuclear powered space flight thesis and that kind of thing. So then switched over to work with the Department of Energy to finish up my dissertation. Exited, went into the defense industry, and I've spent the last 20 years working at small, medium, and large defense contractors on all kinds of things. Worked for DARPA, did a small startup about 10 years ago, exited that, and then went to go work for a test company and a few other organizations. But throughout this period of transition, I was writing articles for the AIAA, for the American Institute of Aeronautics and Astronautics. And one of those articles was about the subject that Lex will talk about today. And so Lex reached out to me recently. He'd read the article about a year and a half ago, and my co-author and I had talked to him as a kind of a student almost of this. But the whole point of that article was to try to bring attention to this idea and this concept that's been around for 40 years. And then Lex, again, reached out a couple months ago and said, hey, I read that and it really inspired me, and I think I want to do something about this. And so I've been helping him get that started.
Very cool, very cool. So as someone who's also very interested in space, I know you mentioned NASA. I think a question I have is, and I guess everyone loves space here. What do you see as the similarities between like the aerospace world and the nuclear world? Obviously you, Brent, have worked sort of at where they overlap in terms of nuclear space travel, but like, do you think there's similar sciences and just approaches to technical thinking, or how do you see those worlds intersecting?
Oh, absolutely. I've spent a career going back and forth between the two worlds, trying to take as many classes as I can while they were available at both the universities I went to. This idea that Lex will talk about shortly started on the ground at the University of Missouri originally 40 years ago as an experiment. It worked, and since then there have been peer-reviewed publications and books and things written about it, but it never really took off industrially. It didn't have a champion as of yet. And so I learned about it through the AIAA. I learned about it through a colleague of mine there up in Canada that did industrial research. He said, I've heard about this thing. It had a few different names and it wasn't really popularized in the literature, but we think it could make a real big difference in terms of the efficiency of the output of a nuclear device. It didn't matter what it was per se. And so I began to research it, and it took me a long time. It took me months of research to understand what it was, that it was real, that it worked, and how it would work. And so I began to put together, an article that was since published by the AIAA and also with Jason Casabri, Professor Jason Casabri from UAH, who, by the way, we were both master's degree students at NASA at the time, 20-something years ago. And so we reconnected over this.
Yeah, wow.
Yeah.
Wow.
It's a small world up in what we do. But he's still working on amazing research in his nuclear field in space, for space applications. And so the difference here with Lex is Lex comes from a very rooted, very ground-based or ocean-based nuclear background with his Navy nuclear background. And he came to me and said, I think this is a really good idea, but I think it could be applied down here on Earth.
Yeah.
Not necessarily to a single mission into deep space that needs a lot of power, but for generating electricity here, right here on Earth for the grid. So with that intro, I think I'll turn it back to Lex.
Yeah, I think that's a good pivot into the question I have, which is, so there's this paper that you'd written for the IAAA, that I guess Lex you read. Tell me a little more. I guess both can answer, maybe Lex or I think both, how this sort of transitioned from a conversation that you guys were having and an idea that you guys were excited about into Solid Atomic.
So I've been looking to form a nuclear company since about 2018, and really poking around the space, and just really like, all right, I want to do something that is really special, and so kind of like I started in like thinking about power to gas. I was like, well, what if we put nuclear reactors in the Gulf of Mexico and generated natural gas or hydrogen from seawater with them instead, and then pipeline that? Because the entire idea was that putting nuclear reactors on land it's kind of not a great idea for a lot of reasons. There's an unbelievable amount of infrastructure required. They're susceptible to like bad weather and natural disasters. And they have like all these kind of like limitations. Oh, and they need tons of cooling, right? And so you have to like locate them where you have lots of cooling. But the ocean, when and I know this from submarine experience, when you're 500 feet underwater, there's no weather. There's you could have a hurricane, a category 5 like rolling over the top of your head, and at 500 feet underwater, it's like, what hurricane? And so it really, to me, it's just like, and the ocean has infinity cooling. You're never not in contact with coolant.
Right.
And so it seems like the perfect place to locate nuclear reactors, and why not just put them there? And so I went up to Huntsville because I read an article about Puff Drive, which is effectively extremely scaled down Project Orion, which is a nuclear bomb powered spacecraft that NASA was working on like 30, 40 years ago, and canceled. And I met with Brent's colleague, Jason Casabri, in his lab, and kind of talked to him about, hey, I'm looking to commercialize a really neat nuclear technology. And Jason was like, well, hey, look at this paper that I co-authored with Brent, and you might want to meet him. And so I looked at the paper and I read it, and I just like practically fell over. I was like, are you kidding me? 60% efficient, and it doesn't have any moving parts,
right?
Like this is a, and I was like, wait. And so, then I emailed Brent, and Brent and I talked for probably like 3 hours straight over, just the nuclear subject.
As any good idea starts, just like diving
right on. And so I and I emailed Brent, and I'm like, all right, so just to clarify, that 60%, the rest of the power, the rest of that energy is being rejected as like heat, right? And I was like, so hypothetically speaking, you could like strap a Carnot cycle to this if you really wanted to, and then make this thing, push this into like the 80% range efficiency. And Brent like nodded on that. And I was like, what?
That's crazy.
Like,
oh my God.
So
theoretically,
right? But we really just started talking about it back and forth, and I was like, and we were like, okay, though the 80s is great, like 60%, that's better. That's like practically double any nuclear technology out there as far as in the field, as far as efficiency goes, and also the simplicity of the device, like the way PIDEC works. And so the way PIDEC, which stands for Photon Intermediate Direct Energy Conversion, the way it works is take a material an excimer material. All right, and excimer takes radiation, emits light, and you put it right next to your fuel with a little photovoltaic cell right in between there.
Yeah.
And this is what Mark Pralis, the original inventor, did at the MER test reactor like 40 years ago. He used xenon as an excimer and opened up a hole in the side of the 10 megawatt MER test reactor, surrounded this box of xenon with solar cells, fired up the reactor, and holy crap, it works.
Yeah.
And, so it's effectively a solid state nuclear reactor, right? That uses a solid heat conductor to just dissipate the remaining heat, but then 60% of that energy comes out in the form of DC as electrons.
Yeah. So what's moderating the fission reaction in a PIDAC system?
So this is a fast reactor, the one that we're particularly working on. So we've got, and as all fast reactors, a big beryllium shield around this thing to reflect all the neutrons back in.
Okay.
Mm-hmm.
And then, or no, go ahead, keep going. I have another question.
Yeah. So, this thing effectively, to dissipate the remaining heat. So beryllium is actually extremely thermally conductive, right? So we just interface the core with, a light electrical insulator with the beryllium shield of this thing, and immersed in a tank of water, this thing conducts all that heat off like no problem, because beryllium, it's effectively equivalent thermal conductivity to aluminum.
Yeah.
So immersed in water, this thing just, all the heat sucks right off this thing, so it stays at like room temperature practically while it's running. So it's a room temperature reactor that outputs at 60% efficiency pure DC, and it's got one moving part, which is the control rod to start it up and shut it down. And since the reactor power level is a function of the photovoltaic output, that's also your nuclear instrument. So your output level tells you what's going on with your fission reaction as well.
Right.
So it's like consolidates instrumentation, it consolidates cooling, it consolidates all the things that are quite frankly terrible about current nuclear reactor designs. And it's like, no, here's just this, so we've got this model for this thing that's just this big, 1 meter diameter, 10-foot tall block that outputs 3 megawatts of DC.
Yeah.
And that's what we've done so far.
Very cool. So my other like relatively technical question I have is just sort of about what makes a good excimer, and I know you said that these experiments were in 40 years ago. What sort of was that a history and a discovery to figure out that you can convert radiation into photons, or was that like known by Madame Curie? Like what sort of the history and the science, and either one of you guys can take it, whoever's more excited, of converting radiation into photons?
Brent's going to take this one.
So I'll do my best. I was not in the field back then, but I've done a bit of reading and talked to Mark Pralis a few times and others. So there were many paths to get to where we are here. It wasn't just linear, but Mark played a critical role in sort of connecting up some early ideas from the original one of the founders of nuclear science, that had this kind of idea of making this is slang, but a nuclear light bulb or a nuclear laser and things like that. Stuff that that has interesting physics, but it didn't really pan out industrially.
Yeah.
And there were many tendrils that kind of came off of that didn't really go anywhere for process chemistry or hydrogen production or desalinization, the kinds of things that Lex was alluding to earlier. But one of them was this little side experiment on the side of the MER reactor that did work. Functionally, I mean, the physics checked out, and it was demonstrated with more primitive materials than we have available today. But in the preceding 30 or 40 years, databases have built up at NASA, by Mark himself, at Department of Energy, or for his own books, and other organizations. There was one that was co-published with him in NATO, actually. And so what I did for our research at the AIAA a couple of years ago, or 3 years ago, was I started looking at these old databases of what was the band gap, the actual photon emission line of these different materials, these different eximers. So we built up a database where we essentially just combined the work of these roughly 3 or 4 different groups, and we built a database of eximers, and we built a database of photovoltaics. So not just silicon or silicon germanium, but exomers going back 40 something plus years that didn't really work out for solar energy, because solar is very broad spectrum. But we worked out all of the band gaps for different semiconductors that could produce a photovoltaic effect. So you have an incident photon, it generates an electron, it generates electricity, and at a certain voltage. And a lot of work had been steered towards diamond type materials that have a very high band gap. They're producing 5+ volts, and that's very exciting physics, but it may not be very practical to engineer something with because the materials just aren't that available.
Sure.
But there was this older material that was produced, I think, in the 70s called zinc selenide. It's kind of a yellow mustard material. It's used industrially for coatings today on glass, for anti-reflective IR coatings, and for IR sensors. And it works very, very well at a particular wavelength of blue light, a little bit like my shirt here. It's colored deep blue, or a little more like Cherenkov blue, like light blue, like Lex's shirt, I think. I can't see because it's kind of dark.
Sure.
And then we found an exomer, cesium iodide, that generally emitted at 2 wavelengths, which is inefficient. But if you add a little bit of sodium to it, it suppresses the higher wavelength, and it goes for the lower, more energetic wavelength. Which is in blue light. And we found that those two overlapped quite closely, and close enough that when I brought this to Mark Frales's attention and some of his students, their eyebrows kind of went up, and they said, oh yeah, when you combine that one material, which I think they were aware of, with this other photovoltaic that they hadn't really thought of, it was a mix and match. And once we did that, we saw an efficiency in the mid 60s. And then there's other losses that occur that are not quantum based, that are laying out the circuits and having methods of taking heat away from the waste heat process, because there's still waste heat generated in this. Sure. It's just not as much. It's about half as much. So we've got a lot of materials in the mid 40s, a few in the 50s, and this one or two. There's a couple that are up here. But there's also no real limit. Like, I was looking at some of the original, what they call W value standard theory, produced in the 1961 by a gentleman named Dr. Platzman. Who writes about these, not about PIDEC, but about how to match these efficiencies between a photovoltaic and an exomer. And really, the quantum efficiencies get much, much higher. And we see this in certain other devices where 60% is nominal. It's not a maximum. And so it's very exciting for the future to think about where this technology might go in other products, other devices. Anything that has an energetic ion that comes out at MeV or close to the speed of light, and then you want to take that energy, convert it to light, and then absorb that in a photovoltaic. There are a lot of applications for this, and so Lex is probably one of the more energetic people pursuing one of the more energetic applications of it. Yeah. So sorry, long history there, but
I
where we got today.
The science is straight. So I have sort of one more follow-up history question, which is these experiments that, I'm sorry, what was his name? Mark?
His name is he's Emeritus Professor Mark Prelas, Prelas, and I'm sorry, I'm blanking on the where he's at currently, but he may be semi-retired now. I'm not sure, but he is an emeritus professor.
Gotcha. So his experiments 40 years ago, what did he pursue a commercial application for this, or what stalled? Was it just sort of like a lack of interest, or what stopped this discovery 40 years ago of this exomer box of xenon from
may I take that one as well? Is that okay? So having talked with him and read his books and things like that, Mark is a professor of physics. He's an experimentalist. He's a pioneer. He is there to go forth and discover new physics. And he discovered, by the way, many other things as he's been working on, and trained loads of PhD students like I once was. So, his career went in another direction, but he did look at the time and talk about this in his books and papers, other applications. And you got to remember, this is the mid to late 80s. So there were other things on the mind of someone that encounters this effect than simple energy production. Hydrogen production, process chemistry like desalinization, water production, and other very interesting physics. There's a lot of really fascinating physics that's happening at the conversion of the ion to the photon to the electron level as well, that they wanted to pursue, and he did pursue, and he published all of that. So he has a volume of work spanning decades that is impressive. And PIDEC is by no means the only thing that he has produced, but that was kind of his focus and where life took him in his career. That being said, he used the tools that were available to try to promote this. He doesn't have a giant marketing budget. And of course, me being a trained mechanical engineer, and you as well, we were taught kind of by rote to think about, okay, we've got energy. let's go put that into heat, and then let's go have a Carnot cycle. That's kind of the 1, 2, 3 steps, sort of like, you know, using Runge-Kutta or Monte Carlo analysis. Those are the tools we're given. Let's go hit that iron with that approach. But what Mark did was, from a basic physics standpoint, is back up and take a very methodical, logical, step-by-step approach. Say, well, why are we taking this super powerful thing and ramming it through a Carnot cycle and losing all that efficiency? And he came out with a solution that at the time was not more efficient. You know, xenon to, I think it was a photodetector, not necessarily a solar cell, but that conversion process was not you know, more than 30% efficient. I don't remember what it was. It was very low, but it worked. That was the key part. And so it took others working elsewhere at NASA and other sources of databases, basically material scientists, many of them, measuring materials. And again, we don't have a complete database of all possible materials. It's largely incomplete. It was just me as a reviewer, not even really a researcher, comparing these different databases that for some reason no one had bothered doing that in a while. It's a lot of very detailed work too, to kind of model all of this, and then set up a giant spreadsheet and then look at it and say, oh, you know, there does happen to be this closeness. And then of course I've been talking with Mark about ways to improve it. There's very advanced physics today called band gap tuning, where you're blending materials to try to match the wavelengths more exactly.
Yeah.
And he kind of helped me know where are the guidelines, where are the cliffs on that. And so there are ways to take the existing material and make it better. You know, you may even approach 70% efficient with basically the same material, just blended in a way that is more efficient. So that he's cognizant of that. But again, it's been 41 years of detailed research. And that's in a nutshell why it just hasn't been taken off. Personally, I asked him, because I was with AIAA at the time, you know, why not space? And his reply was actually fascinating. He said, well, it was a very niche market. And I thought about it, and I was like, you know, you're right. It's one mission, right? I'm talking about one nuclear reactor on one mission. And from his perspective, that's very narrow.
Right.
And so again, it depends on your perspective. You know, how are you looking at this?
Yeah. Yeah, totally. A couple more. I got more questions coming. So I was reading through the technology brief and I saw DC output. And I immediately thought about transmission and application. I know you've talked about hydrogen and desalination. Is the idea to put some load very close to these, or how is transmission from 500 feet under the ocean working in the solid atomic game plan?
Yeah, so it's really kind of whatever the specific application is. You know, to me, ideally, you know, there's terawatts of these things down there, and located with inverters, right, you know, nearby, that are then sending it back to shore in the form, you know, just straight up AC shore power.
Right.
And you know, and to me, locating the inverter as close as possible to the reactor makes the most sense, especially since inverters need lots of cooling too, and that's what you get when you are, you know, greater than 500 feet underwater. So that, you know, that's how I kind of see these pairing up. And but there are also more localized applications where, you know, there's been a lot of underwater DC data centers, where, you know, they're starting to put data centers in the water, because, you know, when you put a data center on land, once again, it's something like 80% of the load of a data center is its cooling, right? And so once again, locating a data center in the ocean makes the perfect sense. It's the most cost-effective way to run a data center. And so if you put you know, strap a nuclear reactor to the side of it, then even better, because you're not suffering from horrible transmission losses.
Right.
And so it's a really, you know, convenient way to kind of output data. And you know, there is gas production as well in there, but, you know, I'm kind of like when you go back and forth and like look at like, all right, why am I making the gas? You know, oh, it's just to make heat somewhere else. But if I can get the electricity for a ridiculously low price, then why would I use the gas to make the heat? Because the electricity is so cheap, I can just heat with electricity, right? And that's been I think this synonymous problem that's been happening everywhere, where there's a lot of green chemistry processes happening, like in refining metals and in metallurgical processes and greater, but like 25% of global carbon emissions are steel and concrete, right? So steel and concrete could both be made green with nuclear energy, right? Concrete, like to reduce lime, it emits a bunch of CO2. Well, you could take that CO2 and then run it through a Sabatier reaction and make natural gas with it, and then use that natural gas to then fire the concrete kiln, in sort of like a combined cycle, right? To make a really low carbon concrete, right? You'd need to run that Sabatier reactor most efficiently. It'd be best to do it on a solid oxide electrolyzer platform with a Sabatier catalyst put on the anode of the cell. And you'd need a lot of DC current. And where do you get a lot of DC current? Nuclear reactors. So, it's sort of just such an elegant solution for whatever process you'd want to run, to have like a DC system. And also DC parallels really well. AC is much harder to parallel. So if you want to build a really big array, paralleling out a bunch of DC reactors is, that's a really compelling proposition.
Yeah, totally.
I could just add real quick, there is ongoing research and development going on in ABB, Hitachi, and Siemens for undersea transformers. For various applications, deep sea and whatnot. That I'm not saying it's a commercial off the shelf product just yet, but there are resources there, and as well as commercial, almost not commodity, but available cables that can go to hundreds of kilovolts, DC or AC, to transmit over miles. So that those are largely solved problems, but it is an important step, like sourcing any vendor network of materials for something like this. If you want to go the AC route and transmit long distances, there are resources out there. And so there's 3 different examples.
Right.
Yeah.
But again, if we decide, or pardon me, if Lex decides not to do that, if he wants to go DC direct, you can go through the cable and take the loss. You're going to lose half or something like that in the transmission by AC. Then there's different trade-offs here that he's accounted for. So, or bring the data center to him, or bring the decarbonization center. There's a lot of really fascinating industrial applications that Mark was writing about 40 years ago, and just in this case, he wasn't writing about them being hundreds of meters under the sea, but it's still the same process.
Yeah, that sort of relates well to, I think, my next question, which is, what are the challenges that have come about with undersea design? I imagine there's some like corrosion issues or something with the salt in the water, but I guess the underwater transformers is kind of new to me. That sounds really cool and exciting. Are there any specific challenges to working underwater that you guys have been running into, or has it been like pretty smooth sailing? No pun intended.
So thanks. That was a good one. So the as far as corrosion issues are concerned, actually, NACE has done such a great job of documenting out corrosion and all the possible ways you can get it, that those aren't really challenges so much as like, okay, what coating do we apply here? What specific blend of alloy do we apply here to protect this thing? So we have our platform design is double jacketed for a secondary containment, right? The core primary containment is in the beryllium shield, and the secondary containment is in a 5000 series aluminum, which is very corrosion resistant to salt water. And then, you throw another coating on top of that, and, you have a really nice setup. And also something that you can go down there with a mini sub, like an ROV, and just ultrasound your secondary containment to make sure that it's perfectly contained. I think that the more significant challenge to going into the ocean is a lot of people in the venture capital tech world don't even understand that that's an entire community of well-established infrastructure, because that's all in the oil and gas space. It's like, if you want to ship to go out and drop something that's thousands and thousands of pounds and then like anchor it to the seafloor and like, you know, connect it up electrically and do all that work. Like there, you know, you call oceaneering, you know, like there's a company, there's actually, and there's Transocean, and there's like 4 companies out there that do that already, you know, and they don't care if it's, you know, BP writing the check or, you know, if it's Solid Atomic writing the check or Southern Energy, you know, they'll go out and do the job. Right. So that's, you know, I think the, you know, one issue that we've run into. Another is I think that it's just like general, like kind of like unknown concerns, you know, like once again, like a lot of people I talk to when I talk about this technology and putting it in the ocean, you know, they kind of immediately go to like, you know, oh, but X, Y, and Z concern. Oh, you know, but it's, you know, if you put it in international waters, security, I'm like, who has the equipment to access that? Like very, you know, that's a very narrow sliver that has that kind of access, you know, you put this thing 1,000 feet down and it's very secure. Right. So that's limited. Oh, well, what about securing an international asset? Well, it's technically not an international asset. It's technically still, you know, coupled to the country that it originated from. And you know, well, what about potential pollution in the seawater? I'm like, well, you know, I know from personal experience, the United States Navy has been operating hundreds of ocean-based nuclear reactors for like 6 decades now, and they haven't really had any problems. You know, because they've designed them really well. You know, the Navy nuclear reactor program in the United States, that's the original program that made the commercialization of nuclear power a thing. Right. You know? And I don't think a lot of people really pay tribute to that, you know, to what like Admiral Rickover and his organization did, is that the Navy really proved nuclear reactors are the best in the ocean. And, you know, they took designs and turned them over to the private sector, the commercial sector, and, you know, companies like Westinghouse and Babcock and Wilcox and GE, they took those designs and they were like, oh, great, we don't want to think about it too hard, scale it up 1,000 times and ship it. You know, and we have now also seen the results of that thinking, and the results is bad reactor designs. You know, oh, the plant's too large, so let's just put the pressurizer below the level of the reactor, 3 Mile Island. Oops. You know, so the, you know, that's kind of small modular reactors in the ocean. It's the OG of reactors.
One of my first jobs I was an intern, a co-op student at Cornell, was at General Electric's power plant manufacturing facility in Schenectady, New York, on nuclear steam turbines, the low pressure section, for a facility that's now operating. And so I just wanted to add, having dealt with the old timers back then, this is like early 90s, like O.J. Simpson era, like that's, you know, White Bronco, that's how long ago this was. Sure. Working for a guy named Bill Addis, who I think is still at General Electric. He's a wonderful manager, and learned a lot about production of these items. And I just wanted to add that GE and their engineers and everyone have a lot of respect for the origins of where this comes from. But yeah, there was a learning process, and over the past decades, about how to make things safer and how to do things better. And they have an amazing track record too, overall. I also wanted to add that going into the ocean, in the deep ocean, actually lightens up or solves or mitigates a lot of problems that land-based do, like Lex had just mentioned. But also, it doesn't absolve you of certain things. So, for example, sourcing HALEU fuel, that's a challenge. That's a challenge for us. That's also, or for Lex, I should say, in terms of solid atomic. But it's also a challenge for other people trying to compete in this space, is getting access to that, you know, 19.5% or even just 10% enriched fuel that is commercially available, but, you know, when you need a lot of it, and we would like to be able to have access to that to actually go run even test reactors. It's not a simple thing to go and get it. So maybe Lex, you could comment a little bit about those challenges. I'm sure you've had others on this podcast talk about it, but
yeah,
maybe
I was
it's worth
actually
reiterating.
personally, I was just up at a conference at MIT, and HALEU was like #1 on a lot of these companies' dockets. There was someone there like on behalf of the DOE talking about the U.S. supply, and it's not the system of production that it needs to be, especially in a post-Russia fuel era. But anyways, yeah, Lex, go ahead. Talk about HALEU.
Yeah. I mean, the main thing when it comes to HALEU is that effectively, whoever's going to get the HALEU in the nuclear fuel community is going to be the first person to raise $1 billion and to then send it to the licensed company producing HALEU already, so that they can put in a dedicated line of centrifuges for it.
Right.
And that's probably the biggest challenge, and that's, not that big of a challenge, but it is one where, everybody's already like spent all their money designing their reactor, paying the Nuclear Regulatory Commission's engineers $300 an hour to vet out their designs. And then to have them come back and be like, no, so that's kind of like a big challenge, is getting HALEU for sure. The other big challenge is this reactor technology to go into manufacturing and full-on production. You need to build a fab. And when I say fab, that's more like a semiconductor industry term. So I spent some time in the semiconductor industry in my career, and fabs are it's effectively the original. It's 3D printing before 3D printing was a thing, right? It's making semiconductors, and so these reactor cores are effectively made using additive manufacturing, and so that is a facility that there's a lot of tooling out there that already exists for what we're doing. In fact, we made a couple of key design decisions that would make the tooling really easy to source, especially even like on the second market, because you might be surprised how much like used or barely used semiconductor manufacturing equipment's on the second market. And so that's a lot of tooling to source and put together and get up and operational, and that's a decent amount of money as well. So really, no matter what, startup costs for nuclear energy are high. But the benefit is really when you go back to look at the bottom line. All right, if I like for instance, NuScale Energy, who I'm about to talk crap about, they spent like $2 billion, right, getting a 60-year-old nuclear reactor design approved by the NRC, right?
I just heard the CTO give a speech about it. Yeah, it was 700 million in 7 years.
Right. Oh, because 700 million. Yeah.
Also, notably,
I saw a publication that said they were close to 2 billion raised or something.
Yeah. Notably, this was for a design approval, not for a license to operate. So
yeah, right. Just for a design approval, right? I mean, and their reactor is effectively it's like a 60-year-old design. It's like an aircraft carrier reactor, effectively, just low enriched, right? And so when you kind of see that from a regulatory point of view from the United States, it's quite frankly, it's pathetic. It is when the United States was electrified, right? When AC was strung up all over this country, the Department of Energy didn't even exist.
Yeah.
Right. They didn't exist until the 70s. Right. And so it's kind of like, that's me being a little conservative right now. So, but the thing is to get to these advanced reactor programs, it is about startup costs, and really, investors are going to have to bet on their horses, so to speak. And, but circulating Carnot cycle reactors there's no way around it. They're just $5,000 a kilowatt. Which is 5 times more expensive than fossil energy, right? It's actually more than 5 times more expensive than fossil energy. but solid state reactors are, like PIDEC technology. It's coming down to like $1,000 to less than $1,000 a kilowatt, amortized over like a 30-year core life.
Wow.
And when you want to talk about competitive economics and, what is green and what is not green, well, $5,000 it might be more green as far as like money is concerned, but it's not more green as far as impact is concerned per kilowatt. The PIDEC technology out there, it is the most environmentally friendly nuclear reactor technology there is. And it's so affordable that when you're talking about combating climate change, like it's just kind of like a slam dunk home run, sort of whatever your sports goal, term is.
Sure. Yeah.
It moves the needle. Yeah. And if I can just add on to that, Carnot cycle has been researched for hundreds of years by many tens of thousands of engineers and scientists. And we're kind of at the limit, the upper limit of what's going to happen with that. You can talk about super heated steam and supercritical turbines and very exotic materials. But at the end of the day, best case scenario, you're getting to maybe 50%, 40%, practically speaking. And in practice, it's much less. Whereas if you look at PIDEC, it starts off around the 40 to 60 range. It starts there and it begins to go higher. And we've seen some theoretical materials that go much higher than 60%. And there's evidence to suggest that there's very little limit when it comes to a quantum efficiency limit as compared to a Carnot limit. There is a limit. It's not going to get you above 100%, of course, but you can start to approach that second tier that is impossible with heat engines. And so it's not so much doing away with nuclear, it's doing away with the boiling of the water and the steam plant and focusing on core. And when you do that, things get much more compact. You start to see economics of scaling up.
Right. Yeah. Okay, so then next question, prototyping. Where are you guys at in terms of building? How's the transition from paper reactor to like actual built system going? Where are you guys at with it? Yeah.
So we've been working for the last 2-3 months now, just getting the reactor on paper. And taking the what that published paper or IAA paper, and then really taking that and saying like, oh yeah, here's a couple of things that needed to be added in, and getting those in and building that all out. So now we're to the point where we have a design that we're like, all right, this needs a little bit more refinement, but we have a pretty good idea of what we're going to do now. And so at this point, we're in fundraising to build the prototype and get the plans finalized and get that done. So really just getting started.
Cool. Yeah, very exciting. And then related, I know, Lex, you mentioned this earlier, but obviously licensing is sort of the question for all of these advanced nuclear projects. I know you said it was just sort of like early design stages, getting all the paper reactor stuff written down and, heat mass balances, all those calculations. Is there any sort of licensing strategy, regulatory strategy? I know you said it'd obviously be underwater, but it would still, I guess, be licensed by the country it's built in, or what's sort of the thinking there when it comes to the regulatory process?
So as far as the regulatory process goes, there's the license to build the design approval, right? That's the big one for everybody, getting their design approved, right? And then there's getting the approval to operate as a commercial power reactor. And that's the hardest one.
Right.
So the NRC, I talked to them a couple of years ago. I met with all of them and about building this advanced reactor technology. And, they were like, oh yeah, here's how our approval process works to get your design approved and marked by the NRC as safe. And then, but then if you want to operate this as a commercial power reactor, that license is like really hard to get. They were like practically bragging to me about how difficult of a license it is to get. And I'm just like, that's not something to brag about. But Then I was like, well, what if I put this reactor 12.1 miles offshore with a submarine power cable running back to land? And they're like, oh yeah, then you don't need that license. You could just plug it in and run it. I was like, woohoo! Score, right? Like,
is that just because the emergency planning zone would be smaller than that, or how is that framed? Sorry.
it's just outside of the international border.
Oh wow.
So outside of the American international border, the NRC has no jurisdiction, and they're only paid to care about their jurisdiction. So it's like if you get your reactor approved as safe by them, right, and get your special material handling license, right, and just those kind of minor licenses to actually assemble these things,
sure.
Those are relatively simple licenses to get.
Yeah.
And with a PIDEC reactor, the solid state reactor, being that you don't have tons of moving parts and coolant, and it's a solid design immersed in water, basically immersed in a giant bathtub of water, right? There's no pumps to analyze for failure because that's all redundant, right? You're controlling just very few control rods, and rod control is extremely well understood and how to do it safely. And those are really simple designs to analyze. So especially, so basically the NRC can analyze, rod control and tell, and write an entire volume about rod control for the reactor. And then they're done.
Yeah.
Then all done, right? Rod control analyzed, we're good to go.
To just add, there is still paperwork. There are other regulators to satisfy and to operate this in a very safe and conscientious manner, but Lex does seem to be onto something here where it may simplify the process or streamline the process to some extent compared to given the operating environment. So,
yeah. Does the IAEA have any jurisdiction on international waters, or is there a governing body?
We're still researching the exact details of who has jurisdiction, but that would be my assumption going into this, is that the IAEA would have a global jurisdiction to start with, and then subsequent to further talks with them. Lex, I don't mean to step on what you're saying, but but the answer I think is yes.
Yeah, it's very muddy water, so to speak, though, as far as because nobody's ever really done it. It hasn't really been talked about, and so and that's actually the best place to be if you're trying to do something that's highly regulated. I remember I did UL approval for solid oxide fuel cell systems in another life.
Yeah.
And that was, I was in charge of doing tons of test engineering and getting that done. And the UL had their pamphlet, or it's I say pamphlet, that's their guidebook for solid oxide approval, for UL approval on a solid oxide fuel cell system. It's like thinner than a children's magazine, right? It is very, very loosely defined. And I effectively helped the UL develop some more standards, to put in there of things to test. But if you go to the UL and you're like, oh, I've got a new toaster design, right, to go into a residential kitchen, they're like, oh, here's the encyclopedia toaster, right? They have this very well-defined, very bureaucratic, cumbersome process for encyclopedia toaster. And, that's, there's trade-offs to that, right? Fortunately, toasters aren't burning people's houses down anymore, right? But also, there's not really any toaster innovation happening, right? They're stuck. They're the way they are, right? And that is a big bummer when it comes to new technology, because when you have that kind of freeze up in the tech chain, the semiconductor industry has not really had that much of that, right? They went out and developed their own standards. They created SEMI to write standards for their own industry, and SEMI still regulates the semiconductor industry, and it's bought into by Samsung and Intel and TSMC. They've all come together and said, all right, these are what the standards are, but those standards haven't shackled innovation in the semiconductor space, which is why we are where we're at in electronics.
Yeah.
you know, in that space. There's been so much innovation. It's just, you know, unbelievable, right? Where the nuclear space has not had that same benefit. You know, we are all out there touting 60-year-old nuclear reactor designs and, you know, things that were conceptualized in the 50s that, you know, we're now like, you know, basically our generation is trying to like dig these things out of the dusty library and, brush off the books and say, let's bring this back.
Right.
And so,
if I may add a little extra information, I worked in semi a bit when I was at Astronics and in the test part of the industry. And so one of the things I noticed was how other groups could come in and help co-write standards. And so, for example, automotive and semiconductor go back, I think, to the origins of semiconductor, maybe the other way around, but they help talk about, you know, what temperature ranges, for example, and how to test and what to look for that works, because they're actually using that in an application. And I think that there are sister agencies and sister industries out there that you know, we're not in a vacuum like space,
Right.
where, you know, you're in space, that there's pretty much one agency really focused on that primarily, and everyone looks to them for guidance. In this case, you know, offshore wind is having a whole a number of things they have to deal with cabling, not to mention the pylons and whatnot. And they're also subject to weather. We aren't, but there's a lot to learn from this other green technology that is in parallel with what Lex is trying to do. So it's always good, I think, to engage these other sources of commentary and regulation. And just to make sure that you have that connection and that you're getting a benefit from that. It certainly helped. The automotive industry has grown volumes because of semiconductor and vice versa. They help each other. I think that there's similar synergies available here. I suspect that there are.
Mm-hmm.
Gotcha. Cool. Yeah. So I think I'll end on sort of giving you guys a big crescendo question moment of what is the next steps? What is the future for Solid Atomic? I know we talked a little about fundraising and prototyping and things, but like just sort of in the moment, what is the vision, both short term, middle term, and long term for Solid Atomic?
Yeah. So for me, I really just want to 10x humanity's energy output.
Yeah.
You know, you look at global energy output on our world and data going back to, you know, 1800s, right? And there's this very clear pattern where energy just is going boom, exponential, right? We are growing as fast as we can. And, you know, doing that on fossil fuels, of course, has been an ecological disaster, right? But we also can't, you know, just stop, and we're not going to. You know, they're effectively energy as, you know, keeps millions of people alive every day. It makes our lives better. There's a published statistic that something like the amount of energy we use in the Western world is the pre-industrial equivalent of having 52 personal servants, like per person, right? So, and there is a huge swath of the population out there that doesn't have energy infrastructure whatsoever. They've got no access to energy, which is kind of like, that's been that's the fundamental baseline to have an industrial economy or an information age economy. Cannot have either of those things without having energy. So by, you know, making a platform that's, you know, basically unbelievably affordable, modular, portable, easy to install, you know, you just put these on a ship and tow them to where whoever wants to install them and like electrify their coastline. And, you know, not to mention the fact that if you look at, you know, Google Maps at night, right, on Google Earth, like most of the lights are on the coasts, right? Like that is the vast majority of energy production, right? You have Palo Verde in Arizona, the nuclear plant, one of the largest ones in the United States, and they ship most of their energy to Los Angeles, right? So that's like 300 miles, right? So we're talking about like, no, let's just transmit the energy like 14 miles, right? To get to where it's needed. And so that's kind of like, for me, the long term, that's the big vision, because like I mentioned earlier, I grew up watching Next Generation and thinking about warp drive and antimatter production and things like that for space. And then once again, I took a class the AIAA a couple of years ago, and effectively the end all be all of space propulsion is antimatter, right? And so how are you going to get antimatter? Well, you either have to make it or you have to mine it. Well, how do you mine it? Well, there may be some antimatter belts out there, we don't know, right? Where we could like collect it. Otherwise, you have to make it. And how are you going to make antimatter? Well, you need to make a lot of energy to make antimatter. What's the best way to make a lot of energy? Nuclear power.
Yep.
So that's kind of, for me, the vision.
Cool. Very exciting. Yeah, well, I'll say thanks again to Brent and Lex for coming on and chatting a little bit about solid atomic. It's been great learning a lot about your guys' process. It seems really exciting and a cool path forward.
Thank you very much, Charlie. Really appreciate you.
Yeah.
Thank you. Thank you very much. It's been a pleasure.
And initiate at least a new approach to the many difficult problems that must be solved in both private and public conversation if the world is to shake off the inertia imposed by fear and is to make positive progress toward peace.